of all, here's where we stand. Okay, we're actually not that bad off because I'd already built in some extra time for lists and sets and maps. So we really didn't need 2 days to go through the list lecture, and we really don't need 2 days to go through sets and maps. In fact, probably next Tuesday, no, I may not get through it all by next Tuesday, but we may start into a brief introduction to Big O next Tuesday. So we're actually still pretty much on course with things. So today what I wanted to do was just finish up with the list lecture, and you kind of went over it in lab yesterday, right, Alan? Did you Sentinel notes and everything? Perfect. Okay. Right. Perfect. Okay. So there was just a couple things I wanted to finish up with Deques and with bad vector usage. So we'll do that first, and then we will move on into using sets. So remember, basically, there's these 3 data structures. You have vectors, you have, we'll actually say lists, vectors, and these strange beasts that we call double-ended queues, DQs. Okay, and we said that lists are good when you need to insert or delete in the middle. So good for insertions and deletions in the middle. And we said that vectors were good for inserts and deletes at the end. But they're bad for inserts and deletes in the middle. And double-ended queues are good for inserts and deletes at the beginning and the end, but they're not good for stuff in the middle. Okay, so I want to actually explain why it's bad for vectors to insert at the beginning. They actually provide an operation that allows you to insert into the front of a vector or to insert into the middle of a vector. But it's a very inefficient operation. So if you have a vector that looks like this, and let's say you had some values in it, and let's say you want to insert into the beginning of that vector. So you want to insert a new element at location 0. That's kind of like the padding thing you did on the exam. What happens, so it's a very simple operation. If you have a vector int say data, then you could declare a iterator, vector int iterator, called vit. So if you're wondering about the abbreviations, usually Dr. Planck uses IT for iterator and then a preceding letter for the first letter of whatever it's going over. So actually probably it would be better if I said dit there for data iterator. So you could insert into this by saying data.insert data.begin, say 10. And what that's going to do is insert 10 at the beginning of that list. See, okay? But the issue, does anyone know what the issue is before I say it? What's going to make it slow? Yep, it's going to have to first move every single entry to one position to the right. So what it's going to first have to do is it's going to have to pull the 1 over by 1, the 2 over by 1, the 3 over by 1, the 6 over by 1, the 8 over by 1, and the 7 over by 1 to make room for it. And in general, if there's n elements in the vector, then we say, we're going to start using this term that it's an order n time insert. Okay, we're going to talk more formally about what I mean by, this is called big O. And what it's just saying is it takes approximately, if you had a polynomial, to express the running time of the thing. So if it was time expressed as n, it would be some function of n. Okay, so we'll get into more detail next week. But basically, it's just saying that the running time of the insert operation is proportional to the number of elements in the vector. That makes it slow. In contrast, if you're so Dr. Planck actually showed that in his notes. So he said that if you try to do it, it's equivalent to this. So a vector is equivalent to doing first a resize operation, then for I equal v size, I down to 0, you have to pull them 1 over before you can do the insert. So it's really slow. Okay? Whereas with a doubly ended queue, it is actually relatively fast. And I'm not going to go into details about how C++ template library implements it, because it's not exactly the way I'm going to show you, but kind of just to give you a general idea of how you could implement a double-ended queue. Let's make it smaller. Let's just make it have 5 elements. Okay, so let's say you start inserting stuff onto the, we'll start with inserting into the back. So we do 3, 6, and 2. Okay, so what happens is it keeps, in effect, conceptually it keeps 2 integer indices, one that points to the front and one that points to the back. And if we now do an insert into the front, what it conceptually does, now it's not quite like this in the STL, but conceptually what it does is it uses a circular vector. It wraps it around. So if I were to insert 2, actually let's insert 10, it would actually put it at location 4. Okay, so it's wrapping it back, and now it's going to put front here. And the idea is that your queue now wraps around to the front. Okay, so that's what makes it efficient, is that it doesn't have to do a resize. It simply inserts before the current element. Okay, so now let's say we did a couple of removals from the front, which would be pop front. It would first remove 10, and it would then update front to point to 3. And if we did another pop front, it would print 3, and it would increment front to point to 1. And now conceptually, these 2 entries, while they still really do have 3 and 10 in them, they're conceptually empty. So again, so this is as though I did a pop front and a pop front. And now if I did a insert, let's say I inserted 8, it again would simply decrement front and put it right there. So you can see that most of the time this is kind of an order 1. Just give me 1 second, Doug. Okay. Most of the time it's an order 1 operation, meaning it's constant time. Now if that queue is full, if the vector is full, then you do have to resize it, and that will cost you. And this is why the STL, the standard template library, does not quite implement it this way. It actually uses what's called a vector of vectors approach, and actually even after I Googled it through the internet, I couldn't find a good description of the algorithm. But they're trying to avoid the issue on an insert where it turns out that the vector is full and they have to resize, that can slow things down if it's a large DQ. So they employ a slightly different approach than this, but conceptually this is how it works. So
do the indices all stay the same as you add to the back, the front, I guess?
what do you mean if you add?
If you do like a push front.
Mm-hmm. Okay, so do another push front.
Right,
so it's actually, shoot, I forget whether push front is defined for a DQ, right, Alan? Yeah. Yes, okay. So, sorry, call this push front. Okay, so you want me to do another push front?
Yeah.
Okay.
And so it would put it at the indice of 4, right?
Yes.
And then point front to 4.
Yes. So in effect what it's doing is it's subtracting 1 from front and then checking to see if it's equal to -1, and if it is, it's setting it to the end of the vector.
So if you call 0, you'll get 10. Basically, the indice 10 is 0. I mean 0
yes. Mm-hmm. You should. Well, he's saying, I'm not sure if you can reference, though, a DQ using vector notation. It doesn't, right, it doesn't really make sense to reference it using vector notation. But you can, Alan. I mean, you can overload the operator to make it work properly.
It is overloaded.
Okay.
But it's gonna give it to you according to the logical position of the vector, not the implementation position.
Right, exactly. So if you did say that I want it, let's say this Q was called D, and you said D of 0 would give you 10, because 10 is the logical, right. Yes. You're not supposed to do that, but it would work. Okay. Conceptually, you're only supposed to be using a doubly ended queue when you're typically either inserting at the front or the back, or removing from the front or the back. Okay. So they gave you that opportunity to index into it, and it would be efficient actually to access them that way. Okay. So now that we've done that, let's actually run a quick timing exercise. So this is something we're going to be doing more throughout the rest of the semester, is actually running bake-offs or races between different algorithms to show you how we are starting to think about efficiency and how there are multiple ways to solve problems, but some ways are more efficient than others. So the bake-off that Dr. Planck came up with was an application called tail, where you want to print out the last n lines of a file. So the one he wrote, you were printing out the last 10 lines of a file. And what he was doing was he implemented using a vector, a list, and a DQ. So he essentially, in the list form, in any of the forms, what he's doing is he's keeping a list that has 10 elements. It's the last 10 lines in the file thus far. So let's say we've read lines 88. Well, initially we read line 1, 2, 3. So initially we're just adding to it. Eventually we get up to line 10 and we read line 11. So when we read line 11, we add line 11 to the back and we delete line 1 from the front. So we always keep, once there's more than 10 lines in our list, we always add a new line to the back and delete a line from the front. And that keeps it at size 10. So I told you that lists and DQs are efficient on this operation because they allow you to efficiently add things to the back and remove from the front. And I said vectors are inefficient because while they're efficient at adding to the back, they're inefficient at removing from the front. Okay, so the code's there. I'm not really going to go over it. Actually, I will just quickly. So basically, what he's doing is reading lines from the file, which from CN, pushing the line onto it, checking to see if the data structure size is greater than 10, and if it is, then he's erasing the first entry. So it's pretty simple. And then at the end, he's simply iterating through the data structure and printing out the lines. Okay? And he wrote up a little shell for doing it. And what he did was he made it pretty enormous. So he has an input.txt file. WC stands for word count, 40,000 lines. Okay, so he has a 40,000 line file, and he concatenated it together, I believe, 18 times. Actually, I think 19 times. So he created a file that, in essence, is 760,000 lines. And then he ran MyTail on it, using first a list, then a vector, and then a DQ. So we'll do that too, and I actually modified it so that, if you look at MyTail list.cpp, I modified it so it's 100. Okay? Because with 10 lines, it doesn't really show it so well, because 10 is just not a very big number. You don't have to move that many elements. But with 100, you're going to have to shift a lot of elements in the vector. So 100 elements, and actually here are the timings. I'd already run them. So right here you can see them. So if you run it on, whoops, I don't have them all. So let me do it again. So we'll first time it on the vector. And it said real-time wall clock time is 2.15 seconds. It took 2.09 seconds of user time. It took 0.013 seconds of system time, where it was in system call time. So roughly speaking, it took about 2.11 seconds overall. Okay, even the real time isn't actually a measure of how long it really took, because it was time sharing the CPU. So the real measure of how long it took is user plus sys time. Okay, so now we'll run it with the list. Okay, how much faster was it, roughly speaking? The list. About 3 times faster using a list. That's pretty fast. I mean, a pretty big savings. Okay, now we'll try it with the DQ. And it's right there with the list, just slightly slower. Okay. In fact, I ran it several times before class, and the list always just got a nose in front of the DQ at the finish line. So the list, at least on my computer, is just marginally faster than a double-ended queue. But they're both quite fast. And the big point is much faster than using a vector. So that hopefully reinforces what I said here, which is that lists and DQs are good for inserts and removals at the beginning and end, and vectors are only good if you're doing it at the end. Okay? So questions? Yes?
Is there a significant difference in element access? Like if you have a random element that you want to access?
Yes. It's a good question. So the question was, is there a significant difference in the access time if you go for a random element? Okay? And the answer is yes. In that case, vectors are your hands down winner, because remember we started talking about this big O. They take constant time. Okay, you can basically, it starts with an address, and it knows what the beginning address of the vector is. It adds, if your reference is I, it essentially says plus I times the size of the type. So like an int is 4. So it's very fast to get there. Whereas with a list, that's going to be order n, because you have to sequentially start at the beginning and count off essentially how many elements. So it's slow. A DQ is also going to be order 1, but not quite as fast as vectors, because the computation is more complicated because front isn't necessarily at location 0 anymore. It's some other place in the vector, so it may take a little longer. So yes, if you're doing So I should say, in addition for good for inserts and deletes at the end, good for random accesses. Okay, bad for random accesses. So with a list, you're typically accessing it in sequential order. Okay, and dequeues are good for random access, although you're not really supposed to use them that way. So the best structure for random access would be a vector. Other questions? Okay. So that was basically from now to the end of the semester. Believe it or not, today is the exact halfway day of the semester. Okay, we're at 7.5 weeks. We have 7.5 weeks to go. For the next 7.5 weeks, we're essentially going to be concentrating on two fundamental types of structures. One is going to be variations on lists, and one is going to be variations on what we call trees, which I'll show you in a moment. Okay, but trees are used to implement sets, multi-sets, which we're going to talk about next, maps, multi-maps. So for the next 7 weeks to the end of the semester, we're essentially going to focus on just two fundamental types of data structures. But these are like two of the three most fundamental data structures in computer science. The third one is graphs, which you will see when you get to 302. I guess array/vector is another fundamental one. So there's kind of four so-called fundamental ones on which most of the data structures and algorithms that we build things are based. Okay, so right now we're kind of going through at a high level how the conceptual implementation of these data structures and how you use them with the STL, the Standard Template Library. And then after we give you the high-level introduction to them, we're going to dive deep and look at how they're actually implemented. So we're going to get closer to the metal, so to speak, and show you how they're implemented. So today, on Tuesday, and probably Thursday of next week, we're kind of at the high-level conceptual thing level for sets, multi-sets, maps, and multi-maps. Okay? So that's what we're moving into. So we already, oops, someone did not correct me. There was a fifth. Well, hash tables, though, are built on arrays and vectors, so I'll take it back. But hash tables, in some sense, are another fundamental data structure. Even though they're built on top of arrays and vectors, they're another fundamental data structure that you use a lot. Okay, so remember when we talked about hash tables, the example I gave you was we want to count up for each word in a file, we want to count the number of times the word in the file occurs. Okay, and hash tables were really good for that, for counting. Like if I want fox occurs 7 times and hound occurs 5 times, hash tables are really good for doing that. Okay, but hash tables, they get their efficiency by storing items in an unordered format. And there's many situations where we want to be able to efficiently retrieve items using finds and deletes, but we want to keep them in an ordered format. Okay, so an example might be, say, mail that's actually sorted by date and time. And you might want, as new mail comes in, you want to keep it in sorted order. And you want to be able to efficiently remove mail when people delete it. If you're moving mail messages to folders, right, that means you're going to have to insert that mail in sorted order into the folder. and you want to see often that mail in sorted order. So in that case, hash tables don't work very well. So my example I'm using is mail with folders. And I want the mail, I want email, and I want items sorted by date time. So primary key date, secondary key time. And for that, what we want to use is some kind of data structure that is going to give us efficient, so what we want is efficient insert, efficient delete, efficient find, and keeps it in sorted order. Okay, it's kind of like going to the car dealership and saying, I want these features on my car. So going to the data structure dealership, and I want these features in my data structure. So there are 4 such data structures supported in the STL. There are sets, or set, there is multi-set, there is map, and there is multi-map. Okay, so set is exactly like the sets you learned. Did anyone learn sets in elementary school? No? Waited till, I guess I was brought up with new math back in the, boy, I'm going to date myself, in the 70s. I believe we learned sets in grade school. When did you first see sets? Middle school? High school? I know you saw, did you not see them before college? Have you not seen them yet?
What do you mean by set?
Yeah, I
A
don't
set, like an intersection. When you say the set A, B, C,
Oh.
and the set like B, E, F, and you do like intersection. Pardon?
I just never remembered where.
Okay. And you can do union and intersect.
I think they tried to teach us, and then we didn't know what they were talking
Okay. So this is what we're talking about here. So the same thing that you learned about with the curly braces and the like. So that's what it's modeled after. So basically, a set is going to allow us to do all those operations efficiently, and it stores a unique set of keys. So there's no duplicates. Okay, a multi-set stores a non-unique set of keys, so it allows a duplication of keys. So keys may be duplicated.
I've seen the multi-sets in CS311, and I think it's like it has like unique set of keys, but like there's like several of them. It's like a given like number.
So it actually is supposed to store each right. So the multi-set implementation for efficiency, so conceptually it stores a non-unique set of keys. You're right. Implementation-wise, the efficient way to represent it is simply keep the key an account of the number of times it appears. So you're right. From an implementation standpoint, that's how you do it. But from a conceptual standpoint, it could be like Brad, Nils, Brad, Smiley, Brad. Whereas a set would be just Brad, Nils, Smiley. Okay, so from a conceptual standpoint, but you're right from an implementation standpoint. Okay, so this is a set, that's a multi-set. Okay, then we have a map, and it stores key value pairs. Keys are unique. And a multi-map also stores key value pairs. And the keys are not unique. Okay, so suppose we had our mail application, and I tell you that the key is date, time, and the value is the message body, whatever that might be. So I want to store my mail application. Which of these do you think I should use? Of these four, date, time, and let's say the time is to the minute, not to the second, but to the minute. Okay, so it might come in as, say, February 24th at 8:03. Okay, so do you think the keys are unique if it's to the minute? Probably a multi-map, right? So there's definitely a possibility that you would have two emails with the same, even to the second, you're probably not safe. You might be safe at the millisecond level. Remember that if you're really writing a mail server for Google, okay, you're going to have to be pretty careful because you might say, even if you were storing it to 1/10 of a second, you might say it's very unlikely that two email messages will come in that both have the same timestamp for 1/10 of a second. Except if you're Google and you're storing billions of email messages, there's a good chance that a few of them agree down to 1/10 of a second, right? So you do have to be very careful when you're designing these things about making sure whether things are really unique or not. So for a mail server, I would probably be actually choosing a multi-map if I was using date time as my key. Okay, so how do these beasties work? Because I think it's important to know it, and I know the notes didn't really go over it. So way they work, remember binary search. Okay, the idea was you took the middle element, and if your target was less than the middle element, you threw away the upper half. And if target was greater than the middle element, you threw away the lower half and looked at the upper half, right? So that was binary search. And the problem with binary search was what?
Had to be sorted.
Had to be sorted, and there's a second problem.
Like being like the same type.
Same type. Okay. So far so I did say it has to keep it sorted. So what I'm doing now also has to keep it sorted, and it's going to have to be of the same type. Can't get away with that. Look at those other three operations. So find is efficiently supported by binary search. What about insert and delete based on what we talked about with vectors? If I need to insert into the front of an array or a vector, is that going to be efficient? No. Order n time, right? So if I used a vector, I'm going to have order n insert, order n delete. Very fast find, if you remember it was log n. But these two operations are slow, and we can do better. Okay, and the way we can do better is we use something called a tree. Okay, so conceptually, let me just draw you first a tree, and then we can talk about it. So it has what's called a root. And then coming off of it, I'm going to show you a binary tree, because each one can have at most 2 children. Okay, so this is a tree. This item is called the root. So the idea is it looks like an inverted tree, right? A tree goes up, it branches out. So it looks a little bit like a tree. If you don't agree, we can disagree. But that's the idea behind it conceptually. So we have a root. And then in a binary tree, it can have, well, this is actually called a binary search tree. It can have up to 2 children, a left child and a right child. And the invariant that we maintain is that the left child must be less than the parent, and the right child must be greater than the parent. Suppose if we say that the keys are unique. Right now we'll say the keys are unique. Okay, if we maintain this invariant, so we call this an invariant, so this is a condition that has to hold, then we can be assured that everything in what we call the left subtree, so this is called a subtree, and this right here is also called a subtree. We know that everything in the left subtree is less than the parent. So everything in the left subtree we know is less than 30, and everything in the right subtree has to be greater than 30. And these are the kinds of things that when you get to CS 311, they will prove or might prove. So they teach you proof techniques. We're not going to go into them in this course. But if I make this assertion, and it's true, then I can prove that everything in the left subtree is less than 30 and everything in the right subtree is greater than 30. Okay, so conceptually, and you notice they don't have to be full. Like down here at the bottom, 8 doesn't have a right child and 25 doesn't have a left child. Okay, so the way that a find works, see, can someone suggest a search strategy if I am looking for 25? Can someone suggest a search strategy?
See if it's less than the root.
See if it's less than the root. So we come in and we're looking for 25. So we first see if 25 is less than the root, and it is.
So then you go down the left branch.
We go down the left branch.
You see if it was less than that.
And it's not.
So you go down the right branch.
So we go down the right branch, and now it's equal. Okay? And if we're looking for something that's not there, let's say it's 26, same thing. 26 is less than 30, so we go to the left branch. Then 26 is greater than 15, so we go to the right branch. Then 26 is greater than 25, so we go down here. And then 26 is less than 27, but we see that 27 doesn't have any children, therefore we know 26 is not in the tree. Okay? Now let's say we were doing insertion instead of the find. Same algorithm, right? We keep doing it, and we find that its location should actually be right there, hanging off of 27 as its left child. Okay. Now deletion's a little more complicated, and I'm going to put that off to later on. It's clearly easy if it's a leaf, right? If it's, we call these things at the bottom that don't have any children, we call these things leaves. So leaves equal a node. So every item is called a node without children. And we say an interior node equals a node with children. So it's easy to delete leaves because they just go away. It turns out it's somewhat difficult to delete interior nodes. So I'm not going to go into it right now. Just want to show you the general idea. Yes?
Is that like what you would use for like, I guess spatial searching? If you have like
Yep. More complicated version of this, but yes, for spatial data that you're trying to do. Like you can do two-dimensional data or three-dimensional data using more complicated versions of these things. Yes. So that's why they're so fundamental, because you use them in a lot of places. Okay. So again, we'll go into this implementation further down the road. I just kind of want you to have this idea that we have this tree structure, and that what it's roughly doing is it's dividing your keys roughly in half, so that roughly half are in the left subtree and roughly half are in the right subtree. And the ones in the left subtree are less than the root, and the ones in the right subtree are greater than the root. So then what makes it complicated is you have to have various dynamic rebalancing algorithms, which is what we'll get into later in the course. Because as you insert keys, one side of the tree could get heavy, right? If I start inserting a lot of keys less than 30, the left subtree kind of gets heavier than the right subtree. And that starts to ruin our performance. So there's dynamic rebalancing algorithms that can actually shift. If the left subtree is starting to get heavy, will actually shift items from the left subtree into the right subtree and promote something from the left subtree to be the root. Okay, so again, that's something we'll get into down the road, not something. So when you see in the notes down the road, you see AVL trees, B plus trees, basic binary search trees. Those are all trees that involve different dynamic rebalancing algorithms. So that's what we'll be talking about when we get to them. Okay, so other questions about this? Okay, so this is dynamic. What's nice is it's dynamic, and it can be shown that if you use good dynamic rebalancing algorithms, that insert, delete, and find can all be done in what we say is order log n time. That is, if there's n keys, you have to do at most log n, visit at most log n nodes in order to determine whether that key is in the tree or not, or to delete the key, or to insert the key. And then there is a way to traverse this thing in sorted order. Okay? It involves something called recursion, which again you see in the notes. Starting right after fall or spring break, we get into recursion. But the basic idea is that you can see that this whole thing is a tree. The left child is also a tree, and the right child is also a tree. So that's kind of what we refer to as recursion, because the tree is itself composed from two trees with similar structure. So it turns out that we could sort this thing if we first followed the algorithm of print everything. Well, let's go to extend this. So we could do a sorted traversal if we first print everything in left subtree, then we print the root, and then we print everything in the right subtree. And in general, if we apply this algorithm at each interior node, you'll see that ultimately it would produce a sorted traversal. Okay, but again, we will put that off for the time being. All I want you to know at this point is it is possible to traverse this puppy in sorted order. And it's actually a rather elegant algorithm for doing so. And you'll learn about that after spring break. Now, having this in mind, we just now want to show you the what's called API, or Application Programmer Interface. So you need to get used to this term, Application Programmer Interface. So it's the set of methods, set of public methods provided by a class. It's typically the set of methods that allow you to manipulate the data. Okay, set of methods provided by a class that allow you to manipulate Okay, so right now we're just kind of getting you familiar with how to use these things. Okay, and that's the focus of the lecture notes that we had today. Okay, so questions about any of this? Okay, think rather than getting into the actual code at this point, I'm going to stop. I know it's about 5 minutes early, but what we will do next time is we will start getting into, let me clear this. We'll just go through some of the examples quickly, and I may actually have a code assessor problem. You first did it in lab on yesterday. You'll be using code assessor probably for your next test on March 12th. In fact, March 11th is when you will be probably doing the programming problem. So I want to get you some practice with code assessor. So probably on Tuesday we'll also have you do a code assessor problem involving sets and or or maps, one or the other. So please try to take a look through the notes. I don't think they're that hard to understand, so I think it's pretty boring for me to give you a blow-by-blow account of what's going on. So most likely I'll do a quick pass over the notes on Tuesday, take questions, and then set you loose on some kind of code assessor problem that gives you some practice with it. Okay? So, have a fun day. Get out there, maybe do some sledding or snowballing, and I'll see you on Tuesday.